Hey everyone, so in this video, I'm going to discuss my solutions to Google Kickstart around V problems. So as I'm recording this video, the contest is still going on, and my rank right now is in top 100. But since I have not solved the last problem complete, so I'm not expecting to be in top 100. So I'm expecting more like top 200 or something. Yeah, should go somewhere close to that. So yeah, I'll start with the first problem. So in the first problem, what you're given is you are given initially a point, and in your input you're given three variables R, A, and B. So what you have to do is you'll draw a circle of radius R on the right, and then you draw a circle on the left, but the radius would be your previous radius times A. Your previous was R, so this would be R times A, right? Then you again repeat this process. You make a circle on the right side again. So this is the circle I'm talking about. So this would be your previous radius divided by B, correct? So every time you make a circle on the right, your radius would be divided by B. And every time you make a circle on the left, your radius would be multiplied by A. So, and when we say division, that division is an integer division. You can see we're taking a flow here. So you won't have any decimal points in your radius. And you have to do this process as long as your radius is non-zero. As soon as it's zero, you uh, anyway cannot make any circles. So yeah, you stop there. Um, so my initial thought on this problem was that I wanted to find some kind of, let's say, a formula or something that how many circles I'm going to draw. And then, make some formula of how I can, add the answer because this is some kind of GP or something. If you think about this, initially radius was R, then this is R times. Actually, it's not because we are doing a floor. So yeah, that logic would not last now. I realize. So yeah, my intuition was that since we're given that the A value is less than equal to half of the B value. So my intuition was that the circle size is going to reduce very fast. And we're given initial radius to be 10 power 5. My assumption was that we won't be doing 10 power 5 number of circles in each test case. I was thinking like more in terms of logarithmic number of circles, something like that. So yes, I didn't have any concrete proof. I didn't think of it, but yeah, that was my intuition. So this is what I did. Had a variable curve which stored the initial radius, and then I had a while loop. This while loop runs as long as my radius is non-zero. And every time I form a circle, I add that to my answer. And I have this flag variable to tell me what side I'm on. So if I'm on a right side currently and I have to go toward the left side, so I'll do a multiply A, right? And this flag switches every time. So yeah, basically you'll compute the new radius based on this flag, and this loop keeps on happening as long as you have some non-zero radius. And finally, you print your answer with a precision of 6 decimal places. So this was enough to pass the first test case. I mean the first problem. Yeah, moving to the next problem. So what you're given this problem is you are given a number and you have to tell how many factors of this number are actually palindromes. So if you look at the test case, 144, then these are the palindrome factors of 144. When I say factors, it's actually a divisor. I'm not talking about prime factors. So 242, you'll have 1, 2, 11, 22, 122, 242 itself. So all these numbers are palindromes and they are a factor of 242 or a divisor, you can say. So you have a total of six numbers, so you'll output six. And your limit on the number is 10 power 10. So what you can do is you can look at all the divisor of this number till the square root of this number. So what I mean to say is, if let's say you have a number 100 or okay 100, then you can simply look for all numbers in range from 1 to 10, because 10 is a square root of 100. Okay, and when I look for every number, so let's say my current number is 1. Okay, then my other, so you can say that if 1 divides 100, then 100 by 1 also divides 100. So you can form pairs like this. So you say 2 divides 100. So 100 divided by 2 also divides 100. Right? This is 50. This is nothing else 50. So yeah. 3 does not divide, so we'll skip 3. 4 divides, yes. So 100 by 4 is also a factor. Since this is a factor, so this will also be a factor. 5 divides, yes. So that would be 100 by 5 and so on. So this would be 20. So if you see this pattern, that if you just look at numbers till the square root, you can get all the divisors of a number. Yeah, this is a very standard concept, but yeah, if you're not aware, then yeah, you can do this. You can look for all the numbers till the square root of that number, and then the other pair would be the number divided by that number, the n divided by this current factor. So yeah, this is what I did. Since this number is up to 10 power 10, the square root of this would be 10 power 5. And we have 100 test cases. So 100 into 10 power 5 is 10 power 7, which is okay. Like in 2 seconds, you can definitely pass that. So yeah, quickly going over my solution. So this was a pretty simple problem, so I was able to solve in like 3 or 4 minutes. So what I'm doing is I'm looping over till the square root of n. Instead of doing square root, I'm just doing this small trick. So if the current number does not divide n, then you skip this number. Otherwise, you have these two numbers, I and n divided by I. And then you check if A is a palindrome, the first number. So yeah, I'm just converting the number to a string and then comparing that string with its reverse. If they are equal, then I say it's a palindrome, otherwise not. So I check it for the first number, then I check it for the second number. And I also make sure that both numbers are not equal. This condition happens when, number is a perfect square. So you don't overcount that number. That's why you'll have this condition B not equal to A. So they should not be equal and should be a palindrome. So then you add it. So this was the second problem. Moving to the third problem, what you're given is you have a kind of, what do you say, a combination lock. So usually you find this kind of lock on like bags or suitcase, right? You'll have numbers from 0 to 9 on those locks. So here you're given a generalized version of that. You have locks which have 0 to d minus 1. So this um, generally you'll have like 3 or 4 different digits, right, in those suitcase or bags. Here you have generalized that as well. So you'll have n different digits, or you should say different dials you can rotate, and each dial can show values from 0 to this d minus 1. And what you essentially want to do is you want to make all of these 0 by rotating them either upward or downward. That's up to you. And how does this whole process works? The process works in the sense that you'll choose some some subsegment, some subarray kind of thing, and then you will move it in one step, you'll move it one step upward or downward. So when you say upward, so your values will increase by one, and if it is d minus one, then the value will become zero. Correct? So that's how like the locks are moving up and down. Um, then how the operations are working, you'll choose a subarray, and then you increase or decrease one by one. This all the locks in that range. Okay. And then for the next iteration, you have to, that it is constrained that you'll have to choose such a subarray which will contain your previous subarray. So let's say if initially I chose this, then I cannot choose this, right? Because this does not overlap the initial subarray you chose. So since we chose this, then yeah, this one is a valid possibility. Even this subarray is a valid possibility. I think you get my point that you'll have to choose something which is overlapping the initial one. So you do this, and you'll have to make this entire sequence to zero. So every digit should be a zero. And the way I did this, so the if you look at the test cases first, your first set would be that your digits would either be a 0 or a 1. And n is also limited to 40. Then your next set is you'll have 40 blocks, and then 10 up to so from 0 to 9 you'll have the digits maximum. And then set number 3, your number of locks or dials is 400, but the value on those dials is from 0 to 10 power 9 minus 1, which is lot. I mean, you cannot loop over this number in one setting at least. Okay. So how did I approach this problem? So my initial thought was I will start from every subarray. So since n is 400, so number of subarrays would be something like 400 and 400. So it's not a lot. So you can loop over every subarray. So let's say I'm currently on this subarray, then I will say that I'm starting from this. And if I'm starting from this, I can. So one other condition was this whole subarray should have same numbers, the starting point I'm talking about. So this is actually not valid. So this could be a valid subarray. And each individual number is a valid subarray also. So this was my initial thought that you start from a subarray with all same digits or same numbers, and then you expand it either to left or right. So I initially was thinking of some greedy approach that let's say I start from here, then I'll have to make it one. Then let's say this is zero, so I'll make it one first so that I can pair it with this number. You can do this in one step. Then your next set would be, so all these are ones. This is also one. So this is like one entire range. Then you have this zero. So you'll make this ones to zero so that you can enclose this zero. You can do that in one operation since G is two. So all these numbers are now zero. This is also zero. So this is now a new set. And since this is a one, I want to make my set to 1, and it is initially 0 now. So it will take me one operation to convert this to 1. So this was my greedy approach. I was working on this and then soon realized that the number of possibilities every time you have is large. Like at every point, you'll have two possibilities, either to make this range equal to the left number or to the right number. Uh, so you cannot solve this you know, in that much time. I mean, you don't have that much time. You'll have like 400 logs. So every time you have two possibilities, and the worst case could go till 2 power like 400. You cannot solve that. in given time frame, obviously. So then the thing is, like I thought of some kind of DP solution to this because when you have like options, then yeah, it's good to think of some DP approach. So you'll have two options, and then you call a recursive DP or iterative DP, whatever you're comfortable with. Uh, for those two, or like if you have two options, you call for those two options. So yeah, I'll show my solutions to this problem. How I found the DP. So I had a DP, a three-dimensional DP, I, J, and K. So so these two dimensions are basically a range. This is the left pointer, and this is the right pointer. And then this third one is actually a flag whose value is either a zero or a one. So what this DP means is this DP means that minimum required. So when you say DP of IJK, so DP of IJK is what is the minimum number of steps it will take you to make all the numbers from I to J same. And if your K is zero, then they should be equal to A of L. I mean the first number. If your K is one, then all of them should be equal to your last number in the range, which is your R. So essentially, if I tell by an example, so let's say this is an example, and I is 1 and J is 3. So this is the range, right? 1, 2, 3. So DP of 1, 3, 0, if I write this here, DP of 1, 3, 0, that would be nothing but to make these numbers equal to 1, since I'm talking about 0, right? So you make them equal to the first number. So I have to make all these 1, and what is the minimum number of required steps to do that? So that is my this DP. If I change it to 1, then that would be, making this whole range 199 equal to this 9. So there should be 999 in the end, right? So that would be the I'll have to find minimum number of steps to do that. So that would be my DP of 131. I hope my DP is clear now. So yeah. Then what did I do? I'll have two options. Either my let's say this is an example. Either my final list would be equal to this one. That would be 1 1 1 1 1 1. Otherwise, it would be equal to this 3. So all these would be 3. Correct? So I'm making two calls here. I have a recursive function go, which I'm calling with 0 to n minus 1 with parameter 0. So I'm trying to make them equal to the first number, all of them. And then this is nothing but, so when you make all of these equal to the first number, since what you want to do is we want to reach all these numbers to 0. So I'll have to also do some extra steps to make that 0. That would be min of, either you go upward or either you go downward. So you take min of those two. And okay, sorry for that. Okay, it was the third problem. Then you'll have another DP, which is nothing but you try to make all the numbers equal to the last one. So you will have this another call. Then you do again the same thing, which is you'll take a minimum of the last number and this t minus last number. So this is the number of steps required to make the last number 0. Not the last number, but all the numbers to 0, because you'll now move all the numbers together. Okay. Right. So how my recursive function is working? So let's say when your L is greater than or equal to R, this is my base case. So when you'll have one or no element in your range. Since you have only one element and this number is always going to be equal to itself, you'll have to do no steps to, in that case, to make it equal to itself. Otherwise, you'll check in your DP that if it is not -1, initially I set it to -1. If it is not -1, it means this state was already computed. So you return the state and then I'm computing the state. So so if x is 0, this flag is 0, it means that I want to make the whole range equal to the first number, which is L, correct? So I'm doing two recursive calls here. If I show you an example, so let's say I make a call initially for this whole range 0 to n minus 1. Then I'll have two options. Either so I make this call for the first number, right? I'm saying that I want to make the whole range equal to 1. I'll have two options in this. So this is the remaining range. In this range, I can do again two things. I can make it equal to the first one, or I can make this equal to the last one. And then for both of those operations, you have to convert it to this one. So again, what I'm doing is L plus 1 to R, I'm making a call with again a 0. So you are making equal to this. So this whole should be a 1 now. Or you're making equal to the last one. So this whole should be a 3 now. You're computing answer for those two steps. And I'm taking my current answer equal to min of those two steps plus uh, the number of steps required, to make this whole range equal to this number. Yeah, then only, right, my whole range would be equal, and uh, I will send it to my parent recursive call. So you take a min of this difference, comma d minus the difference. So that's how you do it for the first number when you want to make this entire thing equal to first number. Other case would be you want to make this whole range equal to this number. So again, you'll have two recursive calls uh, for this part, that you'll make it equal to this number or you make it equal to this number. So these are the two recursive calls. And again, you do the same thing. You'll add the minimum of those two values, either that difference and d minus difference. Again, okay, sorry for that. So finally, your answer would be, the minimum of those two, and you return that answer. You'll have that answer, and then you'll take minimum of that value, comma d minus that value. And this works. So I made a penalty on this. That was like very silly, which was like I forgot to take minimum here. Like I was just adding a of 0. So let's say my range was from 0 to 9, and my a of 0 is 7, then I'm just adding 7 instead of doing 7, minimum of 7 comma 2, 7 comma 3 actually. So yeah, that was like a mistake. So I spent another 7 minutes with the penalty. So this was the third problem, and going toward the last one. So in this problem, what you're given is you're given uh, a grid with some empty spaces and then some obstacles. So every star is an empty space and every hash is an obstacle. Now every star is not just a single empty space. It's like four empty space. So if you think about this, so you'll have these four empty spaces. For another star, you'll have other four empty spaces. For this hash, you'll have those four obstacles. So every point represent four different squares. And what you have to do is you want to find a Hamiltonian cycle, I think, in this graph, Hamiltonian tour actually. So you start from the very first cell and you'll have to come back to this first cell somehow. And you have to visit every non-empty cell, every empty cell, sorry, once. You cannot visit it twice. So that's what Hamiltonian tour is. So in this example, you can just go this way, right? This could be one of the possibilities, or the reverse, right? So you have to print any possible way you can do this. And if it's impossible, you'll say an impossible. So there are two sets here, test cases. The first one basically says that you'll have obstacles at only those positions where this condition is satisfied. So if you think about this, then this is nothing but you'll have star, star, star. Then you'll have like let's say infinite like this. You'll have this now, something like this. Again, you'll have all empty. Then you'll have alternate empty and obstacle kind of thing. So this kind of structure. So note that every star is nothing but four cells, not one cell. So how did I solve this? So I did not solve it for the second test case, which is basically you can have a hash at any place, like you can have it here or here. So I solved this version of the test case, which is test set one. And how I did that was so my approach was I go ahead far as possible, and then I come back. So when I'm saying come back, you can don't think that I'm visiting the same soil twice. So I'm going this, and then I'm coming like this, right? Because you have these four cells. Um, so my greedy approach was I go toward the right first, and then if it is not possible to go right anymore, you go toward down. You go down as much as possible. Uh, and then my third priority was you go. Let me just check. I'm not really sure. I mean, what did I use? So you go right was my first priority. You try to go right. And if it's not possible, then you say, can you go down south? If it's not, then my third condition was you try to go up as much as possible. And finally, my condition was you go left. So my the priorities are I go right first. Then second priority is I try to go south. Third is I try to go up, and then finally the last priority is going left. So you do this recursively. You'll start from 0, 0, and you know have these four calls. Only one of these will be made at each step, and also every time I visit a cell, that cell becomes marked as obstacle now. So you'll never be able to visit that cell. Yeah, you do this operation, and I'm passing my answer as a reference. So I append a new direction every time. And at the end, I know that I'll be here. So yeah, I analyzed this by drawing a few examples. Then I realized that at the end I'll be here, and then I just have to move one step toward the north. So yeah, that's how I solved the first test case. I tried to solve the second test case, but yeah, I don't think I have any logic for that because this greedy does not work on the second test case. Um, so yeah, so that's what my solution was for the fourth problem, first test set. And yeah, I've already crossed the 100 mark. So like now in like 150 something by the end of this contest, I think so. So yeah, that's my solution to this contest. This I think would be very similar to like how my first round went. I had a rank something in line of 120. This would also be something 120, 30, or it should be in 150s. Then yeah, thanks for watching. See you in the next one.